is Bill Bittner, and so today we're going to cover Virtualization Basics, which is a presentation that we recently revamped. We had a version of this that some of you may have seen in the past. This is the new improved version that Jacob Gagnon is going to take you through. So with that, I'll turn it over to Jacob.
All right, thank you, Bill. Yes, my name is Jacob Gagnon, or Gagnon, depends on how true to the French name you want to be. I respond to most things that resemble the last name at all. So, two things you need to know about me. First, I work for ZVM as a CP developer, so that's good because you're all here to learn more about ZVM, so you're in good hands on that front. And also, I'm an identical twin, which I usually mention at the start of this presentation because I've had about 27 years now of practical experience with the idea of perfect replication, which is a very, very important piece to this virtualization puzzle. So you're in good hands for the next hour, and we've got plenty of people in the room to fill in the blanks if you have questions I can't answer. All right, moving on now to the agenda. We got a lot to cover today. What we're going to kind of cover today is really the absolute basics of virtualization, right? We'll talk about what it is in concept, and we'll kind of look at the last several decades to see what it was born out of, right? And so that'll help us frame really how it's relevant today and how it's used today in the market. And then we'll take a deeper dive into the technology. We'll show you how to build it, manage it, monitor it, and we'll kind of take you through from there. Okay, so before we really dive deep, I think it's important for us to start things out on the right foot, because some of you may be coming from a platform other than Z. So I show this nomenclature chart just so that we can kind of get in front of any confusion. For those that might be coming from an Intel or a Power background, you're going to be familiar with the terms that you see on the left-hand side of your screen. And you'll see on the right-hand side of the screen the analogous Z terminology that we use. I'll only point out a couple here, but keep in mind this is a good reference chart for you to take throughout the course of the education and future sessions as well. So a couple things I'll mention. When Z says storage, or when we say storage in Z, what we're really talking about is memory, or what other platforms might refer to as memory. And this isn't really to be confused with what other architectures will call storage, which we will refer to in the Z space as DASD. That stands for Direct Access Storage Devices. And then the other thing that I'll mention that tends to trip people up is how the different platforms will frame the idea of multiprocessing, which is our vehicle for concurrent programming. We in Z tend to refer to it as multiple processors on a single core. Other architectures will flip that and talk to a processor chip that has multiple cores. The difference in terminology there really comes down to a uniqueness of the architecture. But for this presentation, we'll use all the terms you see on the right. All right, so virtualization, what is it and why do we really need to care? Now, the answer to what virtualization is relatively simple to answer, right? At its most basic form, it's the creation of virtual substitutes for real things, right? And the key benefit here is that once you virtualize something, you can replicate it. Now, you'll find that over the course of this presentation, I really like analogies and I like movie references. All right, so I kind of liken it to the Matrix trilogy, if anybody is familiar with that. There's a character in that movie called Agent Smith, and once he's in the Matrix, right, he's in this virtual world, he can replicate himself time and time and time again, which really makes life difficult for Keanu Reeves. Now, we in the real world, we do our best not to make Keanu Reeves' life difficult. So there's a bunch of other real world benefits to virtualization. Like I said, the big piece being that you can, once it's virtualized, you can replicate things, right? And we'll kind of go into some of these benefits you see in some later charts. All right, so to put this into perspective, I think it's best to understand where virtualization kind of came from and where it was born out of. And so to do that, we really need a time warp back to the 1960s. So in 1964, CP40 was released. Now, this is the precursor to ZVM today, and the focus here was on hardware emulation before the real hardware was actually available. And we did this because programmers like me wanted to be able to get some work done before the hardware was available. So emulation is a key concept that we're going to kind of circle back to. But for now, let's kind of go 10 years into the future, right, in the 1970s. Now the shift kind of goes away from emulating the real machine to making the power that these machines delivered available to the masses. A mainframe is not cheap by any means. So virtualization kind of helps justify the expense because you can get a lot more done with that machine. Now, in the 1980s, virtualization is pretty well established, but the machine itself has gotten pretty big. So IBM releases this technology called logical provisioning, or LPAR, to help kind of carve the machine up into more manageable chunks and for use by different operating systems. This is not all that different to the idea of dual booting operating systems on a personal computer. I know at home I run Windows and Linux, so it's not too much of a difference in concept there. Now, between the 80s and 2000s, something really important happened, right? Computing became really cheap, so the computing industry really exploded. Data centers, as a result, got really, really large, and all of a sudden you were paying a lot for raised floor space. So virtualization, again, kind of comes to the rescue here. In that time, you see virtualization take the part of consolidation, being able to take all this workload that's been growing over the last several decades and run it on fewer and fewer machines so that you didn't have to pay for so much raised floor space. Now, in 2014, consolidation projects are pretty much done at this point. So the focus for virtualization and the focus in the industry has been towards streamlining the development process, right? Rethinking what makes up the workloads running on the mainframe and how we can use new things like containerization technologies and microservice architectures to improve the efficiency of our workloads. So if we could break out our DeLorean and kind of look to the future, we see a lot of things on the horizon. We see cloud, quantum, blockchain, all those buzzwords that we hear. And in each of these spaces, virtualization, we can't think of virtualization as a competitor here. We got to think of it as something that can bring these technologies into the existing workflows. Virtualization in ZVM is going to be very important moving to the future of Z. Okay. All right, we got it. We take the real thing, we take the real mainframe, we send it to the matrix, and boom, we got virtualization, right? But to really understand this, we have to understand what we're virtualizing. And what we're virtualizing is an architecture, right? In this case, it's the Z architecture. Now, the Z architecture is defined in this book we call the Principle of Operations. This is the Bible, so to speak, for Z, right? It defines everything that we know and love about the platform. And our job, when we virtualize it, is to make sure that our virtual context is exactly the same, follows the same rules of the road that's laid out in that principle of operations. The key here is that Z as an architecture is valued in the industry. And it's valued because of all the new things we add to it. Z wouldn't exist today if the architecture wasn't robust. And so when we virtualize it, we really have to stay true to form. And so that's why we abide by the rules completely. We don't deviate when we virtualize the POPs in any way. So whose job is it to then create and actually manage these virtual mainframes? The answer there is a hypervisor. Now, a hypervisor is simply put a software layer that takes the real resources, right, and effectively manages the sharing of those resources among the virtual machines. Again, I like analogies, so the way I like to look at it is that a hypervisor is kind of like a parent. They are in charge of actually having the kids. They teach those kids to share with each other. Sometimes those kids want to play with things they don't have, right? And as a parent, you got to get creative because you don't want to disappoint a child. So there's a certain sense of emulating functions. And to kind of complete the picture, sometimes you have to make sure that your kid feels like it's the only kid in the world. So with virtualization, each virtual machine kind of has a level of insulation to it, which we take and try to garner all the benefit from that we can. All right, so to take that, put that to a picture, right, which is worth a lot more than an analogy, I think. We kind of look at this, and this is what we see. When we look at virtualization on Z, this is kind of our picture. So you can see on the bottom, you have the CAC, that's your real Z14, that's the real mainframe in your raised floors. And then you might see what you care about sitting on top, your Linux guests, your ZOS guests, running their applications. And in between, you see a couple layers, ZVM's control program and LPAR. And these are the parents. These are the hypervisors. Now, LPAR is an extension of what we kind of talked about and saw in our timeline chart in the 1980s. And then ZVM's control program is actually what's creating and managing all of your virtual machines, which we'll call guests. And look, sometimes our virtual machines will actually grow up and have children of their own. And so we can actually stack ZVM's control program as a guest of itself, which enables something we call second level virtualization. And that's something that we'll probably explore and actually be able to use in future sessions to kind of work through some of this ZVM virtualization stuff. I think it's time now to kind of take another level set, because now we're starting to talk about resources in a few different contexts, right? There's a lot of views to look at. We've got the real machine, we've got the hypervisors, and we've got the guest. So to keep everything straight, we need to understand that there are different lenses through which you can view a resource. At the lowest layer, you have the real view of things. The people that tend to see real resources are things like our accounting team, right, that's actually buying the mainframe and putting in our race floors. A lot of times, if you're speaking with non-technical family members, you just tell them you work on the mainframe and they picture the actual box, right? So they see the real resource as well. Now, on top of that, once you talk about LPAR, and because LPAR was so successful in the 80s, we can't actually run anything on that bare metal hardware anymore. So when we talk about resources that actually run our work on Z, we tend to talk about logical resources. So our system programmers that are actually working with LPAR and setting up these environments tend to talk about and see things as logical resources. Now, on top of that, when we get to the application developers that are actually writing applications for Z, they're writing things for Linux and ZOS, and so their work is actually getting run on ZVM on a virtual resource. So there's a lot of different views, and the key thing that I want you to take away is that as you go and have conversations with people, and as you continue with this education, try to think about what view you're seeing things through, right? What view of the resource you're talking about, and make sure that lines up with whoever you're talking to. A lot of times confusion arises because one person's view of logical is somebody else's view as virtual resource. Making sure you're on the same page will eliminate that confusion up front. All right, so now you're all here to learn more about ZVM. I've talked to ZVM a little bit so far, but I want to acknowledge it a little more, show you some available things that VM provides. You can read a lot of this chart. I don't want to be a salesperson here for ZVM, but one thing I do want to point out here is the statement that IBM owns the entire Z stack. This is a really important statement, and it's a good part of what makes Z unique, because Z is a top-to-bottom suite of solutions. And so, we own the hardware, we own the hypervisors, we own some of the middleware and even application layers, right? And so what that enables us to do is really bring the hardware and software closer together, handshake information between the different layers, and actually spread out the management tasks of this big virtualization beast among the different layers. So this is what kind of lets us take virtualization and make it competitive in the industry, because we're not doing it alone. So I think that's a really key piece to understand. Let's dive deep and really talk about the virtual machine, what makes it up. And so that virtual machine, again, it's that virtual mainframe that we've been talking about, that virtual resource that's backed by the real thing. And just like the real thing, it has CPU, it has memory, both of those things managed by an operating system. And it connects to a variety of different devices, right? Not unlike your desktops, right? You've got disk and tape drives to hold your permanent storage. You have things like printers and consoles for getting information from and interacting with your virtual machines. And so each virtual machine has all that. Now, when we extend that, we take that visual representation and we just extend it to what we've been talking about. You can actually dispatch thousands of virtual machines with ZVM, right? And each virtual mainframe, each virtual thing is backed by the real resource. And so ZVM acts as the go-between to be that parent and manage the sharing of the real resource to all of that. Now, I'll take a few moments to clarify what I mean as far as how big you can make these environments. I don't want to downplay what you can achieve with virtualization. So when I say thousands of guests, I mean, at least theoretically, 99,999 guests per LPAR. You can stack those up 7 levels high. You can share terabytes of memory, run on dozens of logical cores, thousands of I/O devices. Needless to say, you can get your virtualized configurations pretty large. Now, these are all theoretical limits. We actually start using ZVM. You'll notice that, practically speaking, a lot of these numbers are smaller, but I do want to just kind of emphasize how large things can go. We might tackle some of the more practical limits as we go on with this education. So now we'll break up our virtual machine and talk about each component separately for a bit, right? And so we'll start with processors. A processor is really that source of power for a virtual machine, right? It's the actual thing that runs your workloads. Now, you can kind of view the processor in a couple different contexts. Let's say that ZVM needs to dispatch a virtual machine to execute a task. It's going to do that by running your virtual machine on a logical processor, something that's been carved up by LPAR. So in this sense, ZVM supports logical processors that have been provided to us by LPAR. Now, to that virtual machine that we're dispatching, though, he's running some application code that's being run on a virtual processor. And so when we create virtual machines, we're creating virtual processors for that machine. So when we talk about the application code, to the application, it's running on a virtual resource. So again, trying to keep the layers straight here. Now, ZVM supports several types of processors depending on the workload that you want to run. If you're running Linux on Z, you're going to be running on an IFL engine. For ZOS applications, we have some types like zips and zaps. And it's all about the getting the flavor you need and want. So there's some flexibility there. Now, the other primary component that actually gets carved up by ZVM is memory. Now, this is where your data lives and resides. From an LPAR perspective, you have a chunk of real memory that's broken up among the various logical partitions. So in this sense, it's a finite resource. So to achieve virtualization, we have to be pretty flexible with our memory. In fact, we're so flexible that we'll let virtual machines have pretty much as much memory as they'd like. Now, the way that we can get away with this, having more virtual memory than real memory to back it up, is this concept that we call paging, which is similar to the idea of swapping if you're familiar with Linux. It's the idea that if we need a bit of storage, but we don't have it in our immediate bank of memory, we can actually take something that we're not using, we can page it out to more permanent storage, find what we need, and then bring that page that we need into our memory. So this is what gives us the strength to actually extend this finite resource to the thousands of virtual machines that we can run, and gives us the flexibility to manage memory as we need to for the system. So you can kind of think of memory as the brain of our virtual machine. CPU is the brawn. But without I/O, we can't really connect the two. A desktop is great, but if you can't connect it to a keyboard or a monitor, it's really just an expensive paperweight. When we talk about I/O and ZVM, ZVM will let you use a large variety of different I/O devices for things like storage and displays and printers. But the cool thing with ZVM is that virtualization wouldn't be all that great if you had to have a terminal and a keyboard for each virtual machine. So oftentimes we'll actually fully virtualize I/O devices so that you don't necessarily need the backing of a real resource for every virtual machine. We do some pretty cool things with virtualization in the I/O space to help this scale. So to take that one step further, kind of need to take a step back because there's several flavors, I'll call it, of I/O devices. And knowing the difference is really key in understanding how you have to manage it. We'll start with an analogy here. Let's say that we need a device that's going to get me from my house to the mall because I need to buy a nice bit of jewelry for the missus, right? My parents could give me a car, and then I could go to the mall whenever I wanted to. This would be like dedicating a device to me. But, I'm a family of 4 brothers, so maybe getting each a car is kind of impractical from a cost perspective. So maybe instead I share a family car with my brothers. So it's one car, but we all have to share it. This is kind of like a virtualized device that has been sliced in time. Now, you don't have to slice the device only in time. There's other ways you can slice it, but kind of break the analogy down. Just wait one slide and I'll come back to that thought. Now, at the end of the day, my device is simply meant to get me that nice bit of jewelry for the missus. So one thing I could do is I could shop online, go to Amazon.com, find something and let them figure out whose car is going to deliver me what I need. This is kind of like the concept of a simulated device, right? It gets the job done, but I don't really care how it does it. I just care that I get my shiny bit, my shiny diamond at the end of the day. Now, my preferred device for getting me to the mall is a car. I just can't get my hands on one. Maybe what I have, though, is a bus ticket. Now, it's not a car, but it's got wheels, it's got an engine, hopefully some air conditioning, and get me from point A to point B. So this idea of taking one device and making it feel like an entirely different thing is something that we call emulation. Right, now the key piece here for emulation is that a bus follows the same rules of the road as a car does. If you blindfolded me and put me on a bus, I might believe that it was actually a car. That's a key piece to emulation. So let's take this and apply it to our zSpace now. Let's say that we have 3 Linux guests that are managed by a ZVM hypervisor, and we need to get to some DS8000 storage server. So again, we have things like dedicated devices. We could take a DS8000 storage server and we could completely dedicate it to a Linux guest. That's the easy case. We could also virtualize the disk. Now, this is kind of where we go into virtualizing something in a metric other than time. So we can actually take a DS8000 DASD and we can slice it in space and then give chunks of that DASD to the various Linux guests. And so this would be virtualizing something in space. We can also do things like temporary disk, which is getting something on the fly. We can carve up a DASD as we go and give that to our Linux guests as well. Now, when we talk about simulated devices, we talk about vdisk, right? That's really what we mean when we talk simulated devices in ZVM. So vdisk is, to the guest, a DS8000 server. But in actuality, what it is it's carved up pageable memory. We kind of carve it up from our pageable virtual machines memory, and we make it look like it's a DS8000 server. Now, when we talk about emulated disks in ZVM, we'll use the example of SCSI, right? SCSI appears to ZVM as a fixed block architecture, even though in practicality it's not. So this is the idea of emulation. So to this point with I/O, we've kind of covered the devices themselves, but that's only half the equation, right? We also need the means of connecting these devices to the CAC. Now, I'm not going to go into too much depth on the chart because we could really talk about this for a lot longer than I have time for, but you have to follow a protocol. So we have a few different protocols that we support in FICON, FCP, and PCIe. Just a quick blurb on each. FICON, it's that well-established protocol on Z. It's a command-driven protocol, and it's been in shops for a while. FCP is a protocol that we use specifically for SCSI devices. So if you have SCSI devices, you'll want to get familiar with FCP. And then PCIe is kind of that new kid on the block, more or less. It's a high-speed protocol. That's kind of the blurb on each of the major protocols that we use. Okay, so now at this point with our virtual machine, we have the brain talking to the brawn, right? Our system can actually do a lot of things, which is great. But how do we get our virtual machines out into the world and communicating with other virtual machines? And more importantly, how do we do this without having our data centers look like the mess of wires you see in the top right of your screen? Well, we got to look at the needs of our network, and we got to figure out how we're best going to virtualize our network to meet those needs. So to kind of talk to this, first, let me start by saying that the first thing we need to do is define for each guest a network interface card, which is no different than your personal computers that have their network interface cards that lets you get to the internet. For a virtual machine, you just add a V in front of it. It's a virtual NIC, right? Each one gets one. And that's kind of our hook that's going to get us to the network. Now, where things get interesting is how you actually go from that VNIC to wherever it is that you want to go. And there's a lot of options. So let's walk up through the basic ways you can do it, right? Let's say we need to get to the network. We could take a VNIC and we could attach it directly to an OSA, which is a device that actually lets you get out to the network. It's a physical thing on the mainframe, and that would give us what we need. But that only handles one guest. What about the other 99,998? We can't connect everybody to their own dedicated OSA, because then we get that messy picture that you see right on your screen. So first of all, you can't connect multiple people to an OSA, but you can't do it for the scale of guests that we talk about, right? So one thing that we can do is create a virtual layer called a vSwitch. And so a vSwitch lets you connect multiple guests to this single vSwitch. And then we let this virtualized switch layer handle the routing of traffic. It can connect up to an OSA, and in this way we can kind of overcommit a single OSA device. And if multiple guests need to get out, the vSwitch will handle the traffic. Or if a virtual machine needs to talk to another virtual machine, it can go through the vSwitch. The vSwitch can actually route that message right out to the other guest. So there's a lot of flexibility there. There's also a concept of technology called hypersockets, just another option, another high-speed option for intercache communication. So there's a lot of different flavors and options of networking. What you need for your own configurations really depends on what you're trying to accomplish. But again, you kind of have to look at the needs of your system and kind of map it out and plan it ahead of time and figure out how's best going to be for you to get your guests connected to the network. Okay, so our virtual machine at this point has really come together, right? He can think, he can move. Thanks to the network, he's quite the social butterfly. But now that he can actually handle more, there's a lot of stuff being thrown his way. Things are getting pretty overwhelming. So as functioning human beings, when we have a lot that we are processing at any given time, and we come across something that we might need to remember later, we write it down, right? And so SPOOL kind of lets our virtual machine do the same thing. SPOOL is the intermediary between in-memory information and things that we're going to throw to long-term storage. Think of SPOOL like a mailbox of sorts, right? Things that we may want to look at later, things like dumps of our VM systems, console logs, files from other virtual machines. They all get thrown into this mailbox called SPOOL. And then we can take from that and get rid of the things that we don't need or throw things to long-term storage that we do or that we think it's important. So now with SPOOL and a means of kind of organizing data, our virtual machine is really ready for what the world has in store. But as we know in today's world, what's in store is identity theft and data breaches, right? So what do we do and what can we do to kind of protect our little virtual machine from this? Well, with virtualization, we have an inherent advantage that we can track data down to the machine, right? So there's an inherent security in that, but we don't want to stop there, right? So we also have things like crypto accelerators that exist in each of our cores. And a crypto accelerator is really cool. It helps us offload the difficult math of cryptography onto these dedicated accelerators to do it so that you don't have to waste your CPU cycle that you want running your workloads towards cryptography. I remember when I was in college, I took a course on security engineering, and the talk of the day was always that you can achieve a lot when it comes to security, right? You can really secure your applications, but at a certain level, the cost is just high, and you're going to have to make a balance. So with crypto accelerators, that's kind of IBM's way and solution is saying, well, yeah, you have to make a balance, but we can help you out here. You don't have to take any of that precious processing capability to help make your application secure. We also have dedicated security servers, which you can have to maintain and encrypt your passwords and set rules and roles for your various virtual machine IDs, help you with auditing. That's a tool we call RACF. We put a lot into security and ZVM. All right, so overcommitment. So at this point, what we have is the building blocks that make up our virtual machine, the Legos that make up our virtual machine. And we've got a final picture of what we want things to look like. Now we need to understand the basics of how we get from here to there. To do that, we need to understand one of the largest pillars for virtualization, and that's the idea of overcommitment, which is the idea of doing more with less. And it's based on a really simple idea. And I would say that if I had to pull one thing from the basics of virtualization presentation, I would pull this idea of overcommitment to remember, right? It's this idea that a virtual resource is not going to need 100% of the real resource 100% of the time. In a lot of ways, again, to put an analogy to it, it's like an Airbnb or any other modern day sharing service. I can't use my house 365 days a year because I'm traveling to conferences or I'm on vacation, right? And so whenever I'm not using my house, I can lend my property to someone who can, right? I can rent that out. And so my house is being utilized 100% of the time, just not by me. So this is really that idea of overcommitting a resource. So we'll walk through now each of the main resources and how we go through the overcommitment. So we'll start with CPU. So let's walk through an example. Let's say that we have two logical processors that are defined to a logical partition, and we have a ZVM instance running two Linux guests, and each of those guests has two virtual CPUs. So this configuration, 4 total virtual CPUs backed by 2 logical CPUs, is said to be overcommitted in the processor resource 2-to-1. Now, when Linux guest A has work to do, the hypervisor must look at what's available, and as long as Linux guest B isn't hogging all the logical processing resource, we can dispatch that virtual processor onto a logical processor. So in this small example, you can start to see how you might make some of those decisions. But as the configurations get larger, answering the question of who gets to run on the logical processor and when is actually pretty difficult. So we have kind of a 4-part recipe to help us determine who's on first. It doesn't have to be overly complicated thinking about how this happens at a high level. First thing we need to do is we need to know what LPAR knows. We gather information from the partition. And LPAR knows things like how much real CPU our logical resources are entitled to, how we've been using the resources recently. And then we take that and we combine it with what we as a ZVM hypervisor know. And we as a hypervisor know things like how much a guest should get compared to another guest, what processor types of virtual CPU can or cannot be dispatched on. And then we take all that information and we make a schedule of who gets what and when. And then it's really just a matter of letting our guests run on that resource based on that schedule. Now, the key here is that we're not going to let a guest run for however long he wants. If he gets scheduled and we let him run on the resource and we were to let him run forever, well, we'd lock out our other guests from being able to ever use that resource. So we'll only let him run for a slice of time, which we call a minor time slice. He may use his entire allotment of time. He may not. So for guests that don't need all the time we schedule for them, we'll take that resource, that extra resource, and we'll put it into a pool for other users that are more hungry to use. And so we kind of try to be intelligent how we manage the resource and the dispatching of virtual resource on logical resources. All right, from a memory perspective, we'll again work through another example. Let's say that we have a logical partition that's 1 terabyte. And on top of that, we have ZVM that's running 50 Linux guests, and each of those guests is 50 gigabytes of memory. If you trust my math, that's about 2.5 terabytes for all of our virtual machines, backed by 1 terabyte on the LPAR. So this configuration would be said to be memory overcommitted about 2.5 to 1, which is a common ratio that we see. Now, the way we do this, again, is by paging. So not every guest is going to need everything. So we'll kind of look at what memory for each guest is in use. We don't want to touch that, obviously. And then anything else that's not being used is eligible to be paged out. So then when we have something that we need to grab, we can actually move and page out the not currently in use memory. And if we need to bring something in, we reverse that, we find it, and we bring it into our memory bank. And so I kind of talked about this earlier on. This is just a visual to represent that. All right, we also kind of already talked about overcommitting networks, so I won't spend too much time here. This is just to visualize what I talked about, right? In this example, we have a few different guests that are all connected up to a virtual switch, and that lets us overcommit a single OSA adapter or OSA card to get out the network, right? So this is how we achieve overcommitment from a networking standpoint. All right, so how do you actually build ZVM? Well, we need a few things. Now, what do you mean we need a few things? We've already kind of talked about these building blocks. We have the Legos. What more is there? Well, these things on your screen that you see, they're really things that are going to help us to intelligently build the system, right? It's going to take something that would otherwise be trying to assemble the most complicated IKEA furniture without the instructions, and it's going to take that process and make it more of a paint by number. So when we were kind of developing this presentation, a colleague of mine kind of came up with an analogy that I like to kind of look through these. Now, you do have the LPAR definition, which helps us actually carve up the machine into LPARs, right? But for the other three files, the way I like to think of it is kind of like a modern day phone system. So you have things like your system configuration file, which would define everything that's needed for the actual phone line infrastructure, right? The utility poles, physical telephone lines, switching stations, phone booths, etc. Now, the user directory is kind of that file that forms our phone book and defines everything about the users of our system, their names, their numbers, their addresses. And then the IO/CDS configuration file tells us how to connect the lines so that everybody, our IO configuration itself, all the lines are connected to where they need to go. Now, the key piece, analogy aside, is that our system configuration defines everything about the actual system, the ZVM system configuration. The user directory is where everything gets defined for our users, right? A lot of times we'll find confusion because people think that things should be defined in the user directory that really should be defined in the system configuration and vice versa. So user directory, users, system, config, system, right? So let's look at an example of the system configuration file. Now, there's a lot more that you can configure than what I can show on a single screen, but I tried to choose some interesting things that we kind of touched on or talked about. So here you would set up things like your operator consoles. This is what actually is used to tell CP where to find a console and enables us to see that nice 3270 logo screen for ZVM. Without having an operator console, you can't really interact with a virtual machine. You see the vSwitch definitions, right? This is where we actually set up our virtual network devices. And then you see our CP-owned volumes. These are resident volumes that CP is going to use for a variety of different things. But again, the important piece is this is defining all the things about our system. Nowhere here do you see anything about our users. That happens at the user directory level, right? And so again, you see an example. This is where everything about our initial user's configuration is defined. Usernames, passwords, initial and maximum storage, privilege classes for what brand of commands this user can or cannot use, and a lot more than I can fit on the screen. So this example, we have a user named Linux1, a very, very secure password of mypass. Right? Nobody's ever going to guess that. So he's obviously a very trustworthy user. That little G on the top line, that's going to tell the user that he can only use general class user commands because he's really trustworthy, right? We don't want him to be able to mess with anybody else. So we give him general class user commands. Now, once we kind of like how our users are defined in the user directory, we have a couple tools to help, right? We have a DirectXA utility, which actually takes this human readable code and compiles it to what CP needs to actually apply this. And so you run DirectXA on your user directory to make it live, so to speak. And then you can come up and everything's all fine, right? Now, once you're up, you can still kind of tweak and manage the directory. And so CP has, when we ship the product, we have a directory maintenance or DIRMate tool that you can optionally use. There are other options to help manage the directory, but it's not just coming up. You can tweak things as you go. All right. That brings us to the idea of dynamic resource management. Once you're kind of up and running and you're starting to chug along, things might be going smoothly for you, but then all of a sudden, okay, something's not quite right. Either I need more resource because I didn't really plan enough ahead of time, or I need to make some change for some reason or another. A lot of our things can be adjusted dynamically to help make sure that you don't have to take your system down anytime you have to make a change. And so let's look at this. We'll start with looking at this from a processor standpoint. Right, so there's a lot of different ways that you can manage the CPU resource dynamically without requiring a re-IPL. We have this idea of varying on a processor or varying off a processor or a core of processors. Now, I didn't really touch upon this earlier, but ZVM has support for what's called simultaneous multi-threading. This is the idea that each core can be run single-threaded or double-threaded. It's got 2 threads of execution it can run at any given time. And so CPU will even actually let you dynamically adjust that. If you decide that you want to use simultaneous multi-threading in your configuration, you can actually dynamically switch between running single-threaded or multi-threaded. So there's some dynamic capability there. And then we also have this idea of hybrid dispatch. It's included in CP. You don't have to do anything to enable hybrid dispatch. And so what hybrid dispatch does is it kind of looks at your configuration and how it's running. And it'll say, all right, well, you're using consistently 5 processors, but you have 10 processors defined. Well, we're going to actually put those 5 that you're not using into a sleep state that we call parked. So if you have more processing resource defined, we'll put a select number of it to sleep so that you're only powering the cores that you're using. So we do this dynamically and adjust so that we're meeting your growth, but you're not paying for all the resource that if you don't need to use it, right? All right, from a memory perspective, we can do a lot of the same things. Now, the big thing that I want to highlight here is that you can interact with your system's memory in a couple of different ways. There's a define storage command and a set storage command. And now I'm a processor guy, right? I spend most of my time in the processor tower with CP. And so I frequently forget the difference between when to use a set storage command and when to use a define storage command. And so here's a little trick that I use to remember it. For your VM partitions, your storage is carved up by LPAR. Now, you can set the storage, but only if it's been allocated to you. So whenever you want to make a change to your system's memory configuration, use the set storage command. For your virtual machines, to kind of mess with their storage, you use the define storage command because you've defined that storage when you define the virtual machine. So that's kind of how I keep that straight. There's also some Linux commands that you can actually use to bring memory online or take it offline to Linux if you're running Linux as a guest of VM as well. All right, so in our dynamic world, we do have to admit that there are certain things that just can't prevent you from having to take an outage. The big one being anytime you have to upgrade or service your hardware or software, you usually have to take it down. Now, a lot of these things can be mitigated with careful planning and consideration before we come up, which I'll talk more to later. But for these things that require a planned outage, we don't want to leave you high and dry. And so we actually have a solution that we can use to help you out with the things that you can't adjust dynamically. And that would be the single systems image feature. This kind of allows you to cluster up to 4 ZVM instances, whether that be 4 instances on the same LPAR or across different LPARs or across different CACs, right? You can cluster these together, and this gives us the power to enable something we call LGR, or live guest relocation. Now, what live guest relocation allows you to do is it allows you to take a live running Linux guest from one system to another without having to take that guest down. So this is handy for making sure that any outage to the system, for example, to apply service, doesn't have to necessarily mean you have to take an outage to the guest. All right, so our systems are up and running, configured well, at least we think so. Everything is hunky-dory from a ZVM perspective, so our job's done, right? Well, except not quite, because at the end of the day, if a ZVM system doesn't perform, then it does our clients no good. So we try to do our best to help along the way. And so ZVM, while it's running your virtual machines, is also monitoring your system performance and feeding you back data on how it's doing. And so let's show you a graphic on what that looks like. We have our CP hypervisor, we're running a bunch of guests, and as we're running, we have a performance monitoring that's collecting various things about our guests, about our hypervisor, right? And it's all being collected in the form of raw data. We also have this thing called Performance Toolkit, which will actually take that raw data and reduce it down to human readable content that we can actually look and then view and see how well our guests are doing, how well our system is managing resources, things of that nature. So we can know if we've got to tweak our system in any way, or we know if our system's performing badly. And just like we're there when your system is running and doing well, we're also there if your system, for whatever reason, has to come down. So the key that I want to emphasize is that with EVM, whenever we detect that there's a problem and we won't be able to recover from it, we'll take your system down and capture information on your system so that we can help determine why and we can help diagnose what's causing the problem. With virtualization, we're running workloads that need to be up 99.999% of the time. So if they come down, we don't want it to be that Microsoft blue screen of death situation where you just press the power button and say, oh, I hope it doesn't happen again. So we're there with you. We're capturing the information you need to kind of help us understand what went wrong and led to whatever situation caused us to take an outage. If there is a problem at any point and we have to take a dump, that process is not an instantaneous process. And as you have larger and larger configurations and larger guests, that process will get a little more slow. And so the key to note here is that A, we've taken steps recently to make this process faster so that you don't have to be down for long. But B, the longer that you can wait to take or let your system take a full dump, the more information you're going to have. So as you're exploring with ZVM through this education, right, if you start to take a dump, make sure you complete it if you can afford to, because then you get more information about it to help you make sure it doesn't go wrong again. All right, so just a few more slides to wrap it all up. The theme of this section is really about preparation. First, we'll start with preparation of installation. We spent a lot of time on this graphic. I like to note that we spent probably hours and hours making sure we got this graphic right. It's all about having your ducks in a row before you come up, right? If you know things like what users you want defined and what your network configuration is going to look like, and various things like this, and you have all that set up ahead of time, then it's going to make the process of coming up a lot easier. Because otherwise you're going to come up and you're going to realize that something wasn't quite right, you didn't have something quite right, and you need to come back down, and you play this down and up game. Preparation of installation first. Then there's the service preparation. The theme here is that you need to service VM, right, and you need to plan for that. And so if you know 6 months or a year ahead of time that you're going to be applying service in September, then you can get your clients that are running all aligned to this date, or you can have an SSI, right, and you can plan for migration scenarios to apply this service. If you know it's coming, you better service it and be all set. And then finally, it's preparation of help, right, knowing that you're not going to know everything under the sun. Certainly, this is an education club, right, so a lot of this are good resources for you to go and understand a little more. We have a lot of community forums for our clients so that they can talk with each other about certain things and environments. We have technical publications, red books. You can always contact an IBMer. Knowing where to get help is important. So this is a good reference chart. This is where we reached the end. Hopefully it's been informative. I know we've kept it kind of at a basic high level here. I've done my best to hold up this baby of virtualization like Rafiki from Lion King. I love the analogy, so I'm going to keep saying it as long as I present this. And so now it's time for you to take this and go explore, see what the circle of virtualized life has for you.
All right. Well, thank you very much, Jacob. So with that, I'll thank you all very much, and have a great week.
Thanks for watching. If you enjoyed this video, don't forget to like and subscribe to see more videos like this one. Have a suggestion for another video topic? Feel free to leave a comment below.